So here I am here to present the EViT. It's actually an efficient vision and tracking system for edge deployment. And the authors are Gautham J K, myself, and then Edu Krishnan, Ananya K. J Govin, and Prashant R. Well, coming to the topic, our research actually works with the computer vision. Computer vision enables is a key system for modern systems, and it is used for surveillance, robotics, autonomous vehicles, and all. And the task we are working with is object segmentation and multi-object tracking. And multi-object tracking is there may be multiple objects within the view, and we will be tracking each object and its movements, and a vector will be created. And and all these operations which we discussed above are actually computationally heavy, and we can't use it in a edge device. So, and coming to the real-time performance is also a crucial one if it is used for surveillance and all. So, then coming to the problem statement, we are actually uh, trying to do a comparison between a normal CNN-based model and a vision transformer. Vision transformers have high accuracy and high complexity, that's near to of n square complexity. But coming to the CNN-based models, they are efficient, but there's limited context for it. The number of classes or the scope of those of the CNN models are much more limited. And for a normal vision transformer, considering its complexities of n square, the resolution input, maybe if we are giving an input of 1024 and 1024 pixel, the latency will be at the range of 10 raised to, sorry, 2 raised to 20 or something. So it's much more harder to uh, what to say, much more harder to uh, do the computation within the transformers. So and just we can just understand with the graph the accuracy level we can achieve using CNN models and using the transformers and the computation cost associated with it. And right now we are actually using a baseline of uh, sec former, which we will be discussing right now. This is the baseline backbone of sec former, and we are trying to make it into a system that can be run in edge devices, and will be incorporated with a tracking system. So it's an end-to-end pipeline we are discussing now. Okay, this is the artist of the proposed system where we'll be taking in an RGB image. If it's a video frame, it will be taken in case of frames per second. For each frame will be taken, and the computation will be done. And there it goes to the encoder block, and then it goes to the decoder and post segments post process of post segmentation processing, and we'll be doing appearance embedding and all. Then it goes to the tracker pipeline, and the tracking module does its computation. So we are actually including ASPP. That's actually address spatial pyramidal pooling. It's actually used for deep context analyzing, and it gives a much more higher level of context understanding. And here we are actually focusing on segmentation driven tracking rather than object detection, or I mean detection driven tracking. So when it is coming to segmentation driven tracking, it gives much more pixel level accuracy for tracking context. And this is the feature enhancement and tracking layer we have included within the model. And we'll be using dilated convolutions. Then it enables us to have a multi-scale context and deep feature representations. And for the time being, the implementation of the tracking is done using Kalman filter and IOU based association. It was chosen based on the reduced overhead created by the tracking module. There are several other options such as deep sort or normal sort or both sort or so, and similar such tracking implementation, but those create much more higher uh, overhead, and also it will be creating. But there is one advantage for using deep sort is there is actually a appearance re-identification method which can be used. And coming to experimental overview, we have evaluated the dataset on cityscapes, COCO dataset, COCO 2017 dataset, and MOT 17 and MOT 20 for tracking related benchmarking. And the baseline transformer we have taken is Coma, and there are several implementations of similar to hard and deep so similar implementations were done to check for the comparisons and all. And the metrics we have just used for the segmentation performance is MIOU, and for tracking is MOTA. MOTA is actually multi-object tracking accuracy and IDF1. And for the power and edge deployment capability metrics, we have taken latency, FPS, and power in watts. And the first hypothesis would like to discuss is the efficient models can retain accuracy. The one of the state of the art models is actually SecFormer or SecFormer plus plus. It actually brings in the accuracy or MIOU of 82.8 percentage in real world. But the model we have discussed or we have created is actually bringing in 77.4 percentage, but it is clearly above the autonomous vehicles threshold. So it actually brings in efficient model along with a better accuracy that is actually above the or which can be used for the real world purposes. So there is actually a balance between efficiency and accuracy which can be achieved. And the next thing was the real-time edge deployment is feasible. Normal cases, the vision transformers with a high complexity, time complexity can't be uh, used within a edge devices. This case, the regular case of Raspberry Pi or it's a Nano, it will be having a higher uh, time complexity and it will be having a higher time complexity and low high memory usage. But the model we have brought in is at the size of 17 million parameters. That's actually 90% reduced than the state of the art model, and it works with a latency of 41 milliseconds and creates a FPS or the output video of the real time is actually getting at an 18 FPS. That's actually much higher than uh, most of the models which can produce real time segmentation. And the results of research actually comes at it achieves a 77.4 percentage of MIOU in cityscapes, and autonomous it's actually much higher than the autonomous driving threshold that is 75 percentage. And there's actually just a small difference between the former accuracy MIOU level. That's actually 1.5 percentage points gap, and the tracking performance achieved was 62.1 percentage. That's also a fair uh, performance considering the model size and the computation is thus. And the latency as we discussed, it's actually coming to a range of 41 milliseconds. And the resource usage is actually 648 megabytes. That's almost goes with the RAM limitations of the edge devices we have discussed. That's either the Nano or Raspberry Pi 4. And after integrating tracking, the overhead was only just an increase of 7 milliseconds. So total of 48 milliseconds is the total latency which we uh, got. And coming to the significance of the research is we actually reduce the parameters and enables real-time edge deployment with minimal accuracy loss. And segmentation-based tracking improves robustness in occlusion and crowded scenes. That you can just say we have real-time, we have real-world examples of seeing camera visuals of the what to say shopping malls or railway stations. There will be so many objects or so many similar objects having being in occlusion, and the detection would work with a or will be having a difficult time identifying each object. But for the segmentation, it goes for pixel wise pixel segmentation. So it actually creates or brings in a robust model in occlusion scenarios. And there is a strong the accuracy, latency, and power efficiency is actually much better than any of the models which we have uh, brought into the literature scenario. And there's actually like a scope of future work at bringing in lightweight re-identification for improved tracking, and the knowledge legislation, okay, the KD of this model. And the references we have used is SecFormer, and SecFormer plus plus. Then we have brought in a portion of or the knowledge from the hard edge. That's actually hardware of a design for edge semantic segmentation, and several studies from the sort is also used.